Hi, this is Math 408, something about sphere packing and L functions. Professor Miller, this is lecture 3. And so the big thing we're going to do today is we are going to prove the volume of the n-sphere. And we're going to see some things along the way that we maybe not necessarily need, but they're just good things to see. And so I have written on the board the definition of a chi-squared random variable. This is its density. And the definition of the gamma function. And it's initially defined if the real part of s is greater than 0, but you can extend it to any values of s. And there's a lot of wonderful identities you can prove about the gamma function. There's a lot of facts we're going to need along the way. And so one of the most important ones is the area under the standard normal. So what is the area under the standard normal? 1. So this is the area of under probability distribution is 1. The content of this is that this is the correct normalization for the standard normal, the 1 over square root of 2 pi, to give you an area of 1. And so the idea of the proof is the following. So let I be the integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared dx. So this is the area under what we believe should be the standard normal. And we want to calculate the value of this. And the trick is brilliant. You look at I squared, which is the integral from minus infinity to infinity, integral from minus infinity to infinity, and I'll write x goes from minus infinity, y goes from, or maybe I'll do y and x. And it'll be a 1 over 2 pi e to the negative, oh sorry, that should be an over 2, x squared plus y squared over 2 dx dy. So how would we calculate this integral? Convert to what?
Spherical?
Nope, close. Polar. So eventually you have to learn to listen to the math that's screaming at you. When you see an integrand that depends only on x squared plus y squared, or x squared plus y squared plus z squared, it's screaming at you, convert to polar or spherical or something, and just don't worry about the angles. So we'll let x be r cosine theta, y be r sine theta, and then dx dy becomes r dr d theta. But you should really view this as dr times r d theta. And the reason is we want to have an area. So area is going to be length squared. Theta and d theta are unitless, it's radians. But r times d theta is going to be a magnitude. And the way you prove this is you draw a circle of radius r. Here's an angle theta, here's delta theta, and here's delta r. And you can calculate what is the area in that patch. And you will get pi r plus delta r squared delta theta minus pi r squared. And when the dust settles, the main term is going to be pi r delta r. I'm sorry, 2 pi. I've got to be careful. So what is these over here? It's going to be delta theta over 2 pi. Because I'm looking at what fraction of the object do I have. If delta theta goes all the way around and is 2 pi, then it would be the area of the entire ring. And so when you do the things out, I knew there was a mistake because the 2 wasn't canceling. You'll get that this is equal to pi r delta theta plus pi delta r squared delta theta. And you can see that as delta r and delta theta go to 0, this is going to be something that will become Riemann integrable. But this is going to have an extra delta r, so this is not going to contribute in the limit. So what I'm really doing here is I'm doing a very special case of the Jacobian change of variable formula just for the polar coordinates, because we can do that one without too much trouble. And so going back to our integral I squared is now just the integral theta goes from 0 to 2 pi, integral r goes from 0 to infinity 1 over 2 pi e to the minus r squared over 2 r dr d theta. And this is where you notice that you are living life perfectly, right? The theta integral is trivial to do. It's just going to give you 2 pi, which cancels with the 2 pi there. And the r integral, oh, we have e to the negative r squared over 2. What we would love is when we differentiate that, we would love to have a factor of r floating around, and we do have the factor of r floating around. So this is going to just become 2 pi, 1 over 2 pi, e to the negative r squared over 2. But because of the minus sign, we switch the orders of integration, 0 and infinity, and we get 1. And so we finish the proof of a circle with a square. So has everyone seen this proof? Absolutely brilliant. There are other ways to do this. If you truly understand the gamma factor, I is equal to gamma of some special point. And so your homework is to figure out what point. So what value of s gives you the value of I? Okay. More generally, if you look at moments of the normal, minus infinity to infinity, x to the m times 1 over square root of 2 pi e to the negative x squared over 2 dx. Is this equal to gamma of something? Or maybe gamma of something and some other stuff. Can you find a nice formula for the moments of the normal in terms of the gamma function? Which values of m will be easy to do? Yes? 1. Why is 1 easy?
Because we have an x squared.
We have an x squared and an x. We can integrate nicely.
Yeah.
But I claim that I don't even have to do the integration for 1. So we're integrating from minus infinity to infinity x times 1 over square root of 2 pi e to the negative x squared over 2. What's that integral going to be?
It's an odd function?
It's an odd function, so it's just...
So that's a 0.
Just 0. So in fact, all the odd m's you can do immediately. It's only when m is even that there's going to be anything worth doing. All right, so we now know the formula for the area of a Gaussian. We know that that is equal to 1. So one of the problems I gave you is if xi is a chi-squared random variable with nu I degrees of freedom, then x nu 1 plus x nu 2 is x nu 1 plus nu 2. If you have two chi-squared random variables and you add them, then it's a chi-squared random variable with the degrees of freedom just add. This is a remarkable result. What it means is that if you start off with a chi-squared random variable and you add another one that's independent, it's still chi-squared. The degree changes, but it's still chi-squared. This is, in some sense, a stable distribution. If you take two normals and add them, you get a normal. If you take two Cauchy distributions, if you know what that is, and you add them, you get that. If you take two uniform distributions and add them, you don't get that. Now imagine if you roll a fair die, you get 1, 2, 3, 4, 5, 6 equally likely. If you roll two fair die, you don't get a uniform distribution from 2 to 12. You get a triangle. 1/6 of the time, you're 7, all the way down to 1/36 of the time, you're equal to 2 or 12. So it's very rare for a distribution to keep its form when you keep adding. It's really nice when that property happens. So does anybody have any thoughts about how to do this calculation? Yes?
I just wrote it out.
Okay. Not a bad idea. Roll up the sleeves. Let's start doing the algebra. All right. So proof. So we would have the density is going to be f nu 1 star f nu 2 at x. It's the integral t goes from minus infinity to infinity f nu 1 of t f nu 2 of x minus t dt. Okay. Well, because it's a chi-squared random variable, if t is not 0 or positive, it's going to just have a 0 density. So I don't have to integrate from minus infinity. Where do I have to start my integration at? 0. And then if I look at this piece, once t is greater than x, the integrand is going to be 0, so I only have to integrate up to x. So now we have x occurring as a bound of integration, okay. So we have the constants. So I'm going to just be lazy and write c nu 1, c nu 2 for the two constants. Chalk this up to the pandemic, and I now have to keep myself focused to one blackboard. Space is too precious to write these constants. The functional forms, however, matter. So the first one, I'm going to get t to the nu 1 over 2 minus 1, e to the negative t over 2. And then for the second one, I'll get x minus t to the nu 2 over 2 minus 1, e to the negative x minus t over 2 dt. All right. We can pull a lot of gunk out of the integrand. C nu 1, C nu 2, I can pull that out. E to the negative t over 2, e to the negative negative t over 2, that cancels. We're left with just e to the x over 2 that doesn't depend on t. I can pull that out. And now we have t goes from 0 to x of t to the nu 1 halves minus 1, x minus t to the nu 2 over 2 minus 1 dt. How do we do this integral? So what are your thoughts?
I think substitution.
Excellent. And what did you let u equal?
Tx. No, sorry, t equals ux.
T equals ux. All right, now I have to figure out where the eraser is. And so what you're looking at is, I need to figure out the t dependence. Now the problem is, for those of you at home, can you actually see the light decreasing? Okay, good. Let's see if I can. Okay, so the lights seem to be on some kind of timer with an automatic shut-off, even with somebody underneath them moving. All right, we want to try to pull out how everything depends on x. If I write x as t times u, I can pull the x out? No, I would want to write t as x times u and then pull out the x from this. So I want t to equal u times x. So what's dt going to be? It's going to be u dx.
No,
Sorry. I'm sorry, it's going to be x du. Thank you. Now, t goes from 0 to x. I always like to write something like this down so that I don't make a mistake in my bounds. So if t goes from 0 to x, what does u go from? 0 to 1. And now when I plug that in, I will get c nu 1, c nu 2, e to the negative x halves. The integral u goes from 0 to 1. T is equal to ux, so I'll have a u to the nu 1 over 2 minus 1. And then over here I will have a x to the nu 1 over 2 minus 1, right? From the second factor, I get x minus ux. So I can pull out an x. So I get an x to the new 2 over 2 minus 1, and then I'll get a 1 minus t to the new 2 over 2 minus 1, and then dt is just going to be x du. And so when I look at this, yes?
T should be a U.
This t should be a u, absolutely. Now if I look at this, we can pull all the x stuff outside. We're going to have an x to the new 1 over 2 minus 1, new 2 over 2 minus 1, and an x over here. So we can pull out a x to the new 1 plus new 2 over 2 minus 1. And then we would have an integral, u goes from 0 to 1, of u to the new 1 over 2 minus 1. And we've pulled out this x over here. Okay, how do we evaluate that integral?
You don't have to.
You don't have to. This is the whole theory of normalization constants. We don't need to evaluate this integral. It's some number. So this is going to be some number c, c nu 1, c nu 2, x to the new 1 plus new 2 over 2 minus 1, e to the negative x halves. Because there's no longer any x dependence. It's just some number. Well, if you look at this, this has the same functional form as a chi-squared random variable with nu 1 plus nu 2 degrees of freedom. The only difference is we don't have exactly what the normalization constant is. But since it has to be a probability distribution, it's the probability of x1, x nu 1 plus x nu 2, it has to integrate to 1. So the only possibility is that this has to be c nu 1 plus nu 2. And in fact, you can now use that to figure out exactly what this distribution is, what that integral will be. So you can then solve c is going to be c nu 1 plus nu 2 divided by c nu 1, c nu 2. Does anybody know what distribution this comes into play as? The beta distribution. Excellent. So any questions about this? So this is one of my favorite techniques. I can't speak highly enough about it. Where if you know something integrates to 1, all you have to do is establish the functional form. And once you establish the functional form, you're golden. Okay, any questions about this? I guess the other possibility in class, and if people want to, I'm happy to consider it, is in the future to just actually pick up the laptop and the iPad and just walk down throughout class. So if people want me to do that in the future, I'm happy to do something like that. Okay. So we know chi-squared plus chi-squared is equal to another chi-squared. And I think we did the calculation last time that a normal squared is a chi-squared, right? Which is at least reasonable, because if you square a normal random variable, what kind of numbers will you be getting? Non-negative. Yeah, we can't throw away 0. But yes, it's essentially, it's the...
Probability of getting 0 is 0 anyway.
You haven't taken one of my exams yet, have you?
Guess not.
We use the expanded notion of positive to mean non-negative, yes. So if I keep squaring chi-squared random variables from what we've just shown, I'm sorry, if I keep squaring normal random variables, we know it's going to be chi-squared. So if I look at xi is normal, mean 0, variance 1, x1 squared plus xn squared is going to be a chi-squared random variable with n degrees of freedom. We know that without doing the calculation. We've just proven this. You can, of course, calculate it directly. But this means we actually know now the density for the sum of n normal squares. Why would you ever care about squaring the normal and adding them? You know, just because we're about sphere packing doesn't mean we can't stop and appreciate other parts of mathematics. So why might you care about sums of squares of normals? A hint might be to remember the full name of the department that is sponsoring this course. Statistics. So where would squaring normals and adding them come into play in statistics? Looking at how errors are distributed. And a lot of times you assume errors are normally distributed, and this is how you get a lot of the really good test statistics. And the chi-square distribution turns out to be extremely important. All right, so now that we have this, we'll get rid of all this over here. We'll keep the gamma function and the chi-square distribution on the board. And now what we're going to do is we're going to calculate things related to sums of squares of standard normals. So let's let y, or y sub n, be x1 squared plus xn squared. That's going to be chi-squared with n degrees of freedom. Each xi is each xi is standard normal. So we want to calculate this distribution. So we want to calculate what is the probability that yn is at most y. So this is called the CDF method. It's one of the best methods we have. And what's important is not to stop halfway through. You know, as we go through at some point, we might have to integrate some functions, but eventually we differentiate. All right, so if we want to calculate the probability that yn is at most y, how would I write that?
You could do the sums of all the normals, so the less than y.
Well, but it's the whole sum that matters.
Did you integrate it from negative infinity to y? The chi-square of n.
So one is I could just write it directly in terms of I know it's a chi-squared variable with n degrees of freedom, and I could then integrate directly and calculate it. Yes. What if I want to use the fact that each of the x's are normal? So your answer is absolutely correct. I could write this as an integral from minus infinity to y of chi with n degrees of freedom of, say, t dt. And if I do that, I will get the answer, but I'm not going to get the volume of the sphere. So somehow I want to use the fact that with an integration that will arise, things are constant over the angles and only depend on the radius. So I somehow want an integral depending on x1 through xn. So I'm going to have a large integral, and I want some function So any thoughts on what that function should be and what the region of integration should be?
Always 0, 1 integration.
For each one, or we have n variables. So I want, this is the same as the probability that x1 squared plus xn squared is less than equal to y. If I write it like this, does that make you think of anything?
Circle form?
It makes you think of a circle or a sphere. So I'm integrating this over x1 squared plus xn squared is less than equal to y. And then the function is just going to be multiply the densities of the normals. So then it's just going to become 1 over square root of 2 pi to the n that'll become e to the negative x1 squared plus xn squared over 2. So there's two reasons to do this. One is it's a wonderful result, and the other is to talk about how to think about these problems and how to convert that, well, this is the same as this, and this is making me think of spherical coordinates. Now, I wrote down polar coordinates. I can write down spherical coordinates without too much trouble. I just have to remind myself I'm doing a math class and not a physics class. And for math class, you can even see me pausing. It's phi that comes down from the z-axis and theta that's in the xy plane. Whereas in physics, it is theta that comes down from the z-axis. And I see some of you shaking your heads, correctly so. But I learned it from the physicists first. And so because I learned it from the physicists first, I always have to pause. I will risk saying this because it's being recorded. I love my wife. I love my family. I just wish she had not introduced me to two of her cousins as Danny and Robbie. They're no longer Danny and Robbie. They are Dan. They're old, like my age, almost. They're now Dan and Rob. But because she introduced them as Danny and Robbie, which was what she called them when they were kids, it's hard for me to this day to overcome that. So you really want to think about how things are going. I think this is set up now for like snippets, so you don't have too long of a lecture and you break it up every so often for the home audience. So we want to change to generalized spherical coordinates. So we need a radius r, and how many angles do we need? N minus 1. Let's just, we are not going to have some of the angles theta and some of the angles phi. We're going to have all of the angles theta. We need to calculate the Jacobian. If you want to calculate the Jacobian, it would help to actually know the explicit form of the coordinate transformation so that you could actually take the partial derivatives and that you could then fill this into the matrix. Oh, I know, I'm sorry, but it's a 400 level class. I have to torture you. Okay, then you fill them into the matrix, then you calculate the determinant, right? No one wants to do that. So we're going to bypass it. So here's how it works. We know dx1 to dxn is equal to some function, let's call it g, of r theta 1, theta n minus 1, dr, d theta 1, d theta n minus 1. Do we all agree that it has this functional form? Okay, that's a start. Can you give me one of these variables that's not like the other? Right? The r is very different than the angle. Can you look at this and tell me the r dependence? I'm going to call this function g tilde because g tilde is not long for the world. What's the r dependence here? So if x is in meters, what are the units of dx1 through dxn? Meters to the n. What are the units of dr, d theta 1 to d theta n minus 1? Meters. So what's the only way I can get meters? It's got to be r to the n minus 1. So it's going to be some function g of theta 1 to theta n minus 1, r to the n minus 1, dr, d theta 1, d theta n minus 1. So this is probably the only 400 level math course, I think, in Williams history that starts off on day 1 with the Pythagorean theorem. You know, it seemed a little basic, but this is the dividend of being able to look at something and do this dimensional analysis and see how things depend. If you want, write down the generalized spherical coordinates and do the calculation. Or look at online, which is probably even better, and just see the nightmare of algebra. It all works out in the end, it has to. But this allows us to bypass all of that. When I was an undergraduate, I was fortunate to take 3 math classes with Professor Peter Jones, absolutely wonderful, gifted lecturer, wonderful teacher. And I remember on one of my exams, I think it was in complex, I had done 2.5 pages of painful calculations, and I was still nowhere near finishing the problem. And I wrote, there's got to be a better way to do this. And I stopped and I thought about it, and then there's a few lines answer, if you look at the problem the right way. And he wrote in the margins, it's about time you realize that, Steve. And he was right to put that down there. On an exam, there's often a good way to do a problem. Something that's going to take you 2 hours to burn through is not reasonable in a 50-minute exam with multiple questions. In life, you are not always that lucky. You will not always be in a situation where there is going to be a nice, clean, elegant answer. But more often than not in mathematics, there is. And if you can stop and think about this, we have this wonderful form. So now, if I want to calculate this probability, it is the same as the integral r goes from 0 to how much? So how high can r get?
Y.
Y.
Square root of y.
Yeah, is it y or is it square root of y?
Root Y.
It's root y. I should really write this as this is the square root of y squared. So it's a circle of radius square root of y. So r goes from 0 to square root of y. I have a 1 over 2 pi to the n halves. I have an e to the negative r squared over 2, r to the n minus 1. And now I have all of my angle integration. G theta 1, theta n minus 1, d theta 1, d theta n minus 1. Okay? What is missing right now?
PR.
Okay? Now what's missing? If you want to do this integration, what's missing? Bounds. Okay, good. Now we have bounds. And you have to be careful because maybe we integrate with respect to theta 1 first. Theta 1 could depend on theta 2, theta 3, all the way up to theta n minus 1.
Even if they're all independent?
Well, but you get it, it's how we parameterize things. And again, for this particular problem, all the angles are essentially going to be going either from 0 to 2 pi or 0 to pi, and you have to think about which ones go which way. It's actually, they're all going to be nice independent. They're not going to interfere with each other. But technically, I could have theta 1 depending on theta 2 to theta n minus 1. What can you tell me about this integral?
Oh, it's constant.
It's constant. It's just some number. Does it depend on y at all? No. And so what we get now is the probability that yn is less than or equal to y is equal to some constant times 1 over 2 pi to the n halves. I'll keep that inside, maybe. No, it doesn't matter. E to the negative r squared over 2, r to the n minus 1 dr. And I'll integrate, r goes from 0 to square root of y. Okay? Any thoughts on what we do now? So this is the cumulative distribution function. How do we find the density? Differentiate. So we'll often use a lowercase letter to denote the density. I'm sorry. And now I have to take the derivative of this. So it may have been a while since you've taken a derivative where the bound of integration is actually the variable you're differentiating with respect to, where it's something other than just x or y. You know, the fundamental theorem of calculus, you integrate from, say, 0 to x, and then if you take the derivative with respect to x, you just get the integrand at x. So let's write this very explicitly. It's going to be d by dy, and now we have some density function. Let's call it, you know, fancy f at square root of y minus fancy f at 0, where fancy f is the antiderivative of c 1 over 2 pi to the n halves e to the negative r squared over 2 r to the n minus 1. Does anybody know what the antiderivative is?
Is it a gamma function? Can you just substitute?
Is it the integral?
So you would have to tell me what function has this as its derivative. It's not pleasant. But as soon as you finish taking its antiderivative, what are you going to do? Differentiate. Do we need to know what the antiderivative is? No. Technically, I shouldn't say the. What should I really say here? It's a, but it's not going to matter. So this is going to just be c. And now when I take the derivative, I get my density evaluated at the square root of y. So I get 1 over 2 pi to the n halves. Now the square root of y squared is going to be e to the negative y over 2. Then we have r to the n minus 1, so it's going to be square root of y, so it's going to be y to the n halves n minus 1 over 2. Now when I take the derivative of the square root of y, what do I get when I take the derivative of the square root of y? It'll be 1 half y to the minus 1 half. And when I take the derivative of f of 0, I just get 0. And when you put all the pieces together, you get, you know, c over 2 pi to the n halves, y to the n halves, minus a half, that's just n halves minus 1, e to the negative y over 2.
We've seen this before.
We've seen this before. Where have we seen this?
ChiSquared.
Yeah.
Well, I mean, this matches our expectation because it should be, like, the PDF should be the ChiSquared.
No, because we actually know that the PDF of this is supposed to be the chi-squared. So in some sense, when we got to this point, we could have immediately passed to here without any trouble, without doing this again, because we actually proved that the sum of chi-squares is a chi-squared. So we actually knew this. I didn't have to do this step. I wanted to because it's not that bad, and it just shows you how to do calculations like this. But it wasn't too bad. So we now know exactly what that c is. This implies that c over 2 pi to the n halves is equal to the normalization constant when nu equals n. So it has to be 1 over 2 to the n halves gamma of n halves. All right, so we can actually solve for c very easily from this. Any questions on what we've done so far? Okay, so now let's look back to what we had over here. What do you think this integrand has to be? So this is the challenging part. We're trying to express our integral in terms of the surface area, or in terms of the volume. You know, we know that if we have the surface area, we know how to get from surface area to volume, or volume to surface area. You know, for spheres, it's a very nice shape. If I look at this function is constant on the surfaces. So, in 3 dimensions, it would be constant on the surface of spheres of whatever radius, going from 0 to square root of y. So I claim we can actually rewrite this integral. What should this integral equal geometrically?
The volume of the n sphere?
So in 3 dimensions, so let's say n equals 3. So do you think that this is the volume? Or do you think it's the surface area?
Oh, it would be the surface area.
So it should just be the surface area.
But where's the radius dependence?
Entirely up here.
Oh.
Because if you look at your function, the function doesn't depend on any of the angles. The function only depends on the distance from the origin. Right? And so if I want to calculate, I can look at what is its value on each spherical shell, and then just take all those shells going from 0 up to square root of y.
Oh.
So the surface area is the n sphere or the n minus 1 sphere?
It depends on how you define things. If you're saying the surface area, then I think it would be the surface area of the n sphere if we're defining the n sphere to be x1 squared plus x2 squared plus x3 squared. And back to all the differences between mathematicians and physicists, how do you want to define things? So I will leave this as an exercise for you to finish the calculation. This one I do want you to write up. And let's say homework is due on Monday. It's just, finish the calculation to show that we can now get a formula for the volume from this.
You want to calculate?
Well, we actually know what C is. We know what C is from here.
Yeah.
So you need to somehow go back to this and look at the fact that when you integrate this, you're going to get a surface area. And all of the shells will have the same surface area up to a scaling by the radius. That's what the r to the n minus 1 is coming from. And so what I want you to do is try to finish the proof of this and show how we can get from this to finding a formula for the volume. Or finding a formula for the surface area. The two of them are extremely close. What might be a good value to take for square root of y? What might you want to send y to? So one possibility is setting y to 1. Makes things nice. There's another value of y that might be useful. Why 4?
Then it's,
No, I mean, it's not bad because, square root of 4 is a nice number, but so is the square root of 9 or 16.
Yeah, I thought 1/4, because then it'd be diagonal 1.
Okay, there's that. But there is another value of y, or maybe a value that you might want it to approach. Infinity. So, to me, the most natural things are to take y either to be 1, or y goes to infinity. Well, if y goes to infinity, that probability is just equal to 1. And so then the R integration becomes very nice. And then if that's just the surface area, then we can actually solve for the surface area. And that's what the C is. And so once you know the surface area, can you then find the volume? So I'll leave it to you to finish the details of that. And then once you have that, then compare the volume of the n sphere to the volume of the cube that surrounds it. So if your sphere has radius 1, then you have to do a cube of side length 2. Okay. Any questions on this? Okay, so what I want to do for the last few minutes is just prep something for Friday. So, this was a little bit of a choose your own senior seminar. We chose to do the n-dimensional calculation and then return to the plane. We need to return to the plane. What lattice are we going to study now? Hexagon. So we are going to need to calculate the area of a triangle. Does anybody know how to calculate the area of a triangle? Heron's formula. And so Heron's formula, you can either have the n or not have the n in the name. It doesn't matter. My favorite mathematician is Chebyshev. Russian mathematician, tremendous number of fundamental results in many different fields. I believe there's over 46 accepted spellings of his name when you transliterate into English. I have been trying to encourage people to use different spellings for different theorems of his, so you can quickly say, oh, if I spell Chebyshev this way, it means this theorem. If I spell Chebyshev this way, it means this one. Heron is either with or without an n. So S is the semi-perimeter, A plus B plus C over 2. And then the area, I think it's the square root. Is it S over 2?
Yeah. No,
I think
no,
just S?
S is already over 2.
S is already over 2, right? Okay, good. So it's just S, then S minus A, S minus B, and S minus C. So for homework, prove this. Try to prove it without just Googling the answer.
Would you recommend like just doing like, I don't know.
I deliberately am leaving this vague.
Okay.
Any valid proof I will accept. You should know how to find the area of a triangle, right? This is one of the most fundamental shapes. If you wanted to do tremendous overkill, you could actually set up as an integration problem. Write down the slopes of the two lines, find the antiderivatives, you could do it that way. I just thought of that now. Almost surely that's not how we should teach Heron's formula in schools. But this is something that you've hopefully seen before. Right? How would you prove this? Now, it's important to remark that while I am assigning this to you as a problem, because I think you should know how to do this, we will not use Heron's formula at all. Why will we not use Heron's formula? So what am I going to need when I do the hexagonal lattice? Am I going to need an arbitrary triangle?
Lateral.
I'm only going to need an equilateral triangle. So homework as well, do equilateral. Can somebody give me the most efficient way to do these two homework problems? So homework 1 was to finish the calculation. Homework 2 is to prove Heron's formula. Homework 3 is to do the equilateral triangle. Yes?
Wait, do you not want us to do the gamma function thing? I equals gamma x, whatever.
Which one was that?
So I was,
Oh, yes, I'm sorry, that's right. That was homework problem 0, thank you. Yes, homework problem 0 was the gamma function one, yes. What's the easiest way to do these two problems? To do Heron's formula and then the formula for the equilateral triangle.
Heron first.
Do Heron first and then specialize, right? So if you want to do the least amount of work, prove Heron, because you have to prove Heron, and then specialize and get the area of the equilateral triangle. Why might this not be a good way of doing it? It's fine. It's going to be the most efficient way to do the homework. Yeah, so in fact, the equilateral triangle can be proven without going through the full argument that you need for Heron. And this is something that is often lost, especially when you're reading papers, and we'll end after this, and I know I'm a minute or two over. Frequently, people who are writing papers, especially the world experts, they use the most powerful versions of theorems that they know. But a lot of times for the application, you actually don't need the strongest version. You just need something weaker. And it's a great idea to get a sense of the depth of an argument. I was co-supervising a thesis years ago at Princeton, and the student had to use Bayes inequality for Kloosterman sums. And the paper that she was reading had the world best bound. But she did not understand the proof of that. And I told her, don't worry, I don't understand the proof of that either. But I had two advisors, and one of my advisors, Professor Vanyans, taught me how to count on my fingers. And he taught me how to get order of magnitude estimates and how to do some of these calculations to just get sometimes just a power savings. And so you're not going to get the square root savings that the more advanced algebraic geometry machinery gets you, but you can get a savings of 1/4, which is all that you need for this problem. You don't need the elephant gun for this one. And it's a good sense when you're doing math to get a sense of just how deep is the result, how much do you really need to know to make it work. All right, so I am going to stop here.